Hello everyone, thank you for coming here, and also thanks for connected. So it's really my pleasure to introduce you Camilla Coletti. She's leading a research line in Pisa on 2D material engineering, and also the Center for Nanotechnology Innovation. So Camilla, thank you very much for being here. The stage is yours.
So thank you, Daniele, and really it's very nice for me to be here today because I'm since 2011 in IIT, and this is the first time that I really get the opportunity to fully see all the robotic lines and what they do, and it's really good because although, as you will see, we do completely different things, the idea here is to find a synergy and to try to find ways to collaborate, which I think could be beneficial for IIT. So as Danielle introduced, I'm leading the 2D materials engineering research line, which, as the name says, works with 2D materials. And you might have heard a lot about 2D materials, possibly have an opinion about whether they're useful or not. And today what I'm going to do is trying to introduce those that are not really acquainted with 2D materials on what they are and why they might be useful, then go a bit more in depth on what my research line does, and then see whether we find some ideas. So this is the research center where we work, and any one of you interested in coming and visiting us is very welcome. We are in Pisa. It's actually a pretty old research center of IIT, and currently we are not so many as you are, guys. It's probably 45, 50 people or something like this. And the location is a pretty ancient, originally monastery, where Napoleon actually settled the Scuola Normale Superiore. So it's actually a very ancient and prestigious place, but it's also very old and falling apart. And as you might imagine, in Italy, when you need to renovate things that are very precious from an historical point of view, it's not straightforward. So if you come, some parts are new, some parts are very old, but it's nice anyway. It's not far from the Leaning Tower, and as you might know, there are two centers in Pisa, so sometimes there is confusion, which center is this? So this is the real Pisa center, and then there is one that you know maybe better that is in Ponte. So this is the Scuola Normale, let's say, hosted center. The other one is the Sant'Anna hosted center. And yeah, basically, the only problem we have is that, as Daniele probably saw when he visited us, we have very, very big hallways, very kind of ancient building style, very small rooms. So the laboratories are actually pretty small, and we have useless, not useless, it's good to meet and for a coffee, but well, anyway. So let's keep going. I've also had the opportunity to lead this Graphene flagship initiative on the last 4 or 5 years. As you might have heard, there were different flagships that were funded about 10 years ago. And the one that we got funded significantly is the Graphene flagship. So we had 8 PI, and among these 8 PI, you might know some faces that are IIT people that work as PI within the flagship. And then there are professors that are affiliated. Actually, Marco Polini was within IIT, but now not anymore, to IIT and conducting their research as IIT within the Graphene flagship. So it was actually a pretty huge effort IIT-wise. And the main idea was to try to find a way to make 2D material useful and impacting industry from basic science really into well, directly companies and so on. And somehow I say this succeeded. We have seen within IIT the startup of Bidimensional that actually is a very nice, would say, product of the flagship. And like Bidimensional, there have been many others coming in within the Graphene flagship, and there have been quite a few products that came out. We'll discuss about this. About my research activities, we do synthesize 2D materials. So our expertise, we are material scientists as of base, and we are basically try to make these 2D materials as best as possible with the best property that we can achieve, and find then both the understanding on the fundamentals, because that is the spring that allows us to move towards application. So we synthesize them, investigate the fundamental properties, and then try to find application in different fields. The one where we mostly work are photonics, sensings. We do also biomedical devices, and the very up and running quantum technologies that now is a magic word in our field, at least. Is something that will keep us going for the next years. So these are our lab. Since you're not there, I try to show a bit what we do. So that's synthesis lab. We have 2 of them where we have furnaces. Within the furnaces, we synthesize the 2D materials. Okay, so they're just so-called reactors where we have gases at high temperature, and in this way we synthesize the material. Then there are laboratories for routine characterization. These are usually twofold. Either we have very, very quick and dirty way of characterizing, which are either AFM, atomic force microscopy, spectroscopic tools like Raman, which allow you to just put the material under and see, okay, is there, well, as you might know, 2D materials are invisible by definition. So you really need some tools to see how they are, what's the quality. So we use these tools. And then we have more sophisticated ones, which are under ultra high vacuum. And those are, well, this guy, for example, over here, where we put our materials in ultra high vacuum and then study the structural, electronic, and chemical composition of the material in a much more refined way, which helps us to understand the fundamental properties, because those are, well, the tools with which you really can see how they behave, how they could be at their best. But then we know that when you actually put them in air, they're going to behave differently. So we also have these tools to characterize them in air. And then, of course, we have a clean room to fabricate our devices, either, you know, transistors or this kind of device. That's what we do. And then we characterize our device. For example, photodetectors, transistors, as I said, with photoelectrical measurement. Okay, that's basically the full chain of what we do in my group. We have several collaborations. We usually go to synchrotron to measure the property of the material. So we use very, very powerful light to study our material. And then our industrial collaboration, as of today, I listed here the most important, are mostly, as you might see, with photonics and, well, semiconducting companies, because that's where the materials that we synthesize find the most natural application. Well, yeah, that's a very classical slide. I'm sorry if you already know everything about it, but as you might know, graphene, it's a very recent material. It was discovered only in 2004. There are different opinions about how and who was the first. Okay, as of today, we know that 2 guys that were working in Manchester, 2 Russian scientists won the Nobel Prize for graphene discovery, but it was 2004, namely a Friday night in Manchester, where they did a pretty standard and easy experiment, which is Scotch tape and graphite powder. So basically a pencil, and then they isolated graphene, found it with a microscope, and started to study it. Okay, but the pretty nice thing is that if you think about it, graphene stacked one on top of the other, the single layer of carbon atoms is graphite. So the usual definition is, what is graphene? Is a single layer of graphite. Okay, so everyone had it in their hands since elementary school. It's the most democratic material ever. Every one of us had a bit of graphene powder in their hands at some point. Then if you actually wrap it in a ball, it's a fullerene. And then if you roll it, it's a carbon nanotube. So graphene might be seen as the constituent of all this material, yet it was the last to be discovered. Just because scientists thought graphene to be non-existent in nature because thermodynamically unstable. That means that the common knowledge up to the 80s was that if you actually isolate a 2D material from the 3D counterpart, it would just wrap up, roll into itself, and stop being bidimensional and start being 3-dimensional. Okay, so many of us didn't even, well, I was born, but I was still very little in the 80s, didn't even think about doing it at the earlier time because it was no way to find something like this. But then some scientists started to say, oh, but really a flat layer of carbon nanotubes would have such fantastic properties, we should try. And then some people already working with a carbon-based material started to give it a try. And in a way, it was demonstrated that it's not true. It doesn't roll up. Graphene exists in 2 dimensions. It's very stable. It's not thermodynamically unstable. And that's the big jump that was done, because starting from that moment, all the researchers started to study 2D materials. materials because they said, oh, we can really have materials that are confined into dimension. And so to have quantum confinement, we can have different properties. It sounds kind of difficult, but it is so. If you actually say something that is 3D and you just slice it down to the atomic thickness, then the properties are going to be different because of quantum confinement. That's what you have. And what makes graphene special, okay, it's a bit of a technical slide, but I won't go too much into detail. It's just that if you take, okay, I haven't said something very basic. Graphene is basically constituted by carbon atoms that are disposed in a honeycomb lattice, okay? So we have just honeycomb of carbon atoms. Now, if we look at the carbon atom itself, we are going to have in plane sp2 orbitals and out of plane pz orbitals. What makes graphene special is that we have the sigma bond, the in-plane bonds that give the mechanical resistance, and the pz, okay, so the pi bond that actually are half-filled and give the electrical conductivity, which is very famous for graphene. Okay, so that's basically how it is structured. Now, we will see that because of this peculiar structural characteristic, it also a lot of interesting properties. Indeed, the first one is the electronic dispersion. So if you ever happen to study the electronic properties of material, you always end up looking in a book and seeing some lines that just show, you know, oh, silicon is a semiconductor, so we have a valence band, you know, a conduction band, and we have a gap, is direct and indirect, and everything else. What is graphene? Graphene has actually a very peculiar dispersion of the electronic bands, and you have a linear relation. Okay, and that's what makes graphene special. It's this kind of energy momentum relation that if we plot the electronic bands is linear for low energy. So in this where there is an, okay, and this is what really makes graphene special, because that means that the electrons, the carriers, in our case also the holes, because graphene is bipolar, as both electron and holes that conduct very well, have a zero effective mass. That means that these particles move within this material at incredible velocities, which can be, okay, have been often said similar to those of light. Okay, it's not really true, but actually they are very high velocities. Okay, so mobilities of electrons in graphene can very easily go on 600,000 centimeters squared over volt per second, which is a very, very high velocity. Okay, so this guy moved ballistic. That's basically the major point. Other properties of graphene. So we talk about the electronics, so this incredible electrical conductivity. Then we have also very interesting topological property, and that's where the story becomes interesting. It's because you have a mixture of different properties within one material. It's not only electronically interesting, but it's, of course, the thinnest material is practically transparent because basically it absorbs only 2.0% of visible light. So indeed, it's not 100% transparent. If you put it on top of proper substrate, you can actually tell with a very trained eye that there is graphene, but it's very, very thin. But not being only thin, as I said before, tribology makes a difference. It's very strong. Often it has been said that it's stronger than steel, or, you know, like graphene is like, oh, this super strong material, but at the same time is very flexible. These two properties don't go together. You might know that something is either very strong, so very high modulus, young modulus, or it's very flexible. The two things together hardly go together. In graphene, paradoxically, they do go together. And then you would ask me, okay, so graphene was discovered in 2004. Okay, that's more than 18 years. Why we don't have something very good done with this material that is super flexible, up to 20% on its own length, so you can actually stretch it up to that, and also super hard, so harder than diamond and so on. Well, because it's very difficult to make graphene of such a high quality over a large scale. These properties have all been predicted and tested on very tiny bits of material, which are usually the diameter of a hair. So pretty useless, right? When you start to do scaling up, then the properties go down. But the paradox of the Nobel Prize Committee that actually
then I will go into the Nobel Prize. But what they said is like, oh, there is the graphene hammock. The graphene hammock would be a graphene layer that would actually be able to hold a cat of 4 kilos, being invisible, so we would have a floating cat there. And the net itself, the hammock itself, weighing less than a whisker of the cat. It's pretty, right? But that's how they started to attract the interest of people. Oh, that's really cool. We should do really cool things with this. And one other thing is that graphene doesn't only have, probably I have not all the right slides here, but I'm just saying on top of my mind, so sorry for those connected if I do not show everything that I say, but the thermal conductivity is also very good. It's not only electrically conductive, but also very well thermally conductive. So basically it dissipates very well. Okay, so just 6 years later, the Nobel Prize in Physics was awarded. It was the 5th of October 2010. It was Max Planck Institute, was working in graphene, and I was thinking, okay, now I need a plan B. I can't keep working on graphene because it's on the Nobel Prize. No, I'm kidding. But with my friends, we were just, postdocs saying, okay, yeah, I mean, guys, we need to change. Actually, that wasn't really true because a lot of money was coming into. So when I was working in Max Planck in 2010, it was a very still small community. We weren't so many working on graphene. In Italy, there was basically almost nothing. But because the money was still not going around the day after the Nobel Prize, it was crazy. I was a postdoc. I got interviewed, ended up on a newspaper in Germany, interviewed in German. My German was really, really horrible, but they managed to get some sense in what I said. And I was like, wow, that's a new era. And it was actually going to be something very nice to be working in at that time because you were still in the environment. The environment was small. You knew everyone pretty much by name. When the areas are still like coming up, you're like very, very friend with everyone. And then it started to become a huge field with a lot of newcomers, and then of course you lose track of whatever it starts to happen because it becomes huge, it explodes. But well, those very few years, I remember exactly what was the novelty that year, and so on and so forth, and really convinced me that maybe graphene was the field to stay in for a few years more. Okay, that's going back. And that's going forward, but yes. Okay, so now we fast forward to 2023, which is actually this year. Wow. And we find some products of graphene in the market. Not as many as people would like to have seen, not as many as people expected somehow naively to see, but if one goes through history and knows a bit of material science, we always know that from when the material gets isolated to when there is the first product, it's not so fast. Okay, if we look back and think about 1700 or something like this, definitely technology is slower, so cannot be as fast as today. But we are talking here about a material that is basically invisible, very hard to manage, very hard to synthesize, so well, it might not be so easy to get products working in a short time. Many products you might have heard of are where graphene is actually embedded within another material. So you have a composite material where graphene is just added in small or bigger amounts to change the final material. So for example, we have tires that have better grip, less wear, so they resist more. We have coatings for racing because they're like very good for thermal dissipation and things like this. Also, the Momo Design helmet, IIT and Graphene Labs was basically spray coating of the vetroresin, well, the name of the inner part of the helmet, and this is to increase the resistance to shock. And basically the test proved that in case of some kind of edge shock, it was more resistant. For the rest, not. If you just bump like this, not. But it's very good for thermal dissipation. So the main thing that people that buys it tells is that, well, yeah, it's good because you don't sweat so much. So that's basically the main outcome of a graphene material where electrons go ballistic. Well, it's a helmet, or, you know, like a composite in a tire, the racket of Djokovic that in the first year was always saying, oh, yeah, it's a graphene enhanced racket because it's a better maneuverability, or, you
impress better strength to the ball and so on. I'm not a tennis player, so I don't really know if that is true, but they are all products which we could define low tech in the sense that there is no high technology. I mean, it's nothing where you would expect to see graphene. When it came out, it became a playground for physicists. People started to say, oh, we have ballistic electrons, we can finally prove some things that were only predicted during Einstein time, relativity, quantum mechanics. We have finally things to prove it. And actually, it has been a playground to prove some things that couldn't be proved otherwise. But if you look at products, they're pretty not sophisticated as shoes, antibacterial shoes. I mean, things like this. And that's because producing graphene is very complicated. And the easiest way to produce it is to do it top down. That means taking graphite and breaking it up until you get the single layer or down there. And that's how these products are done, always with inks, with graphene produced top down, and so in liquid phase, okay? What we do is something different, and it's a real production of graphene bottom up with precursor trying to replicate the little flakes that were originally isolated. I will show you how. So for several high-tech applications, we need high-quality scalable graphene, and that's where we try to come in. So how to obtain graphene? That's one of the major points. Historically, in 2004, the method I described you before is the mechanical exfoliation method. I take a pencil, I take the tip of the pencil, it's graphite. Actually, it doesn't really work. That's what, I mean, honestly, I've done it in elementary school with some kids, and you see something that looks like graphene. Then Kostya Novoselov, one of the 2 Nobel Prize, told me, no, it doesn't work. We try to measure the electronic property are not the same. You really need some specific graphite. But anyway, that's the story. You take graphite, you use Scotch tape, no fancy Scotch tape, and then you basically just exfoliate multiple times. So you just like this, multiple times, until you get a single layer. You really don't know when you get the single layer. It's just experience. Then you press it on top a substrate where it becomes visible, go with the microscope, search for it, say, oh, this is thicker, this is thinner, because the transparency makes the optical contrast. Then you finally say, oh, maybe this could be a single layer. You go there and measure it. The Nobel Prize often was said, oh, it's too early. Why giving a Nobel Prize only after 6 years? It might be a shared thought and a very legitimate one. Well, it's not because they did such a stupid experiment. I mean, stupid in the sense that it's not difficult, but it's because they studied the property and so what the material was holding, and then it just changed the mentality of us material scientists thinking, oh, we can do everything single layer. Sorry. But anyway, this material was the most expensive material on Earth in 2008. I don't remember how many millions, but it was incredibly expensive. Why? Not because graphite, not because Scotch tape, because the amount of hours that a student or a worker would have to spend to find it and actually isolate it. It was the most expensive material. So we had to find a way to make it more cheaper and scalable. And I would say the easiest way, as I just mentioned, is the top-down approach. So we do a chemical approach, like reduction of graphene oxide or liquid phase exfoliation. Liquid phase exfoliation is actually the most common one, the one that the dimensional, for example, have used. They are used worldwide. Here, of course, it comes also a lot of confusion because many companies said they had graphene, they really didn't have graphene, they just had graphite. And then the properties are not so good, and then, oh, graphene doesn't do anything, we tried it, it's just this shit. Well, it depends on the quality of the material. It's not so easy to really define how, what is the quality. You need to be an expert user, but sometimes there is misconception about what graphene is. Graphene is really the single layer. Up to 2, 3, 4 layers, 5, maximum 10, you still have some kind of confinement. Up to then, more than 10 layers graphite. It's just graphite. It doesn't change
much. Then also mechanically, you lose all the properties because you have friction, you have a lubricant behavior, right? Because graphite is known to slide. We don't have van der Waals forces. That's why we can, we don't have covalent bond. We have van der Waals forces between one layer and the other layer. That's why you can exfoliate. You don't need to break bonds, okay? Bonds are only in plane. There are no out of plane bonds. Only van der Waals. And that's why basically you can have lubricant material that typically also exfoliable as 2D material. But when you start to make it thicker, it's just breaking more easily. Okay, these are like the technique to get graphene in liquid, and those are the technique we actually use. The reactor I was talking to you about before are these, pretty much. You can either synthesize directly on insulators, which is a bit more difficult, or you actually synthesize on metals, which, as you might imagine, are catalytically active, so it's a bit easier. So that's how you get this guy, this graphene, to be very similar to that exfoliated guy that is very small, though. So that's scalable and high quality. And that's what we have been trying to do for the past many years. And I would say now, finally, this material is mature. This material was mature much earlier. That's why we see products nowadays, because it was mature and it was incorporated in products. This material starts to be mature now. So we would expect, if anything has to come out, to be in the next years. Okay, so a bit more boring stuff. I will try not to make it too boring. And if there is any question, curiosity, even things you think are stupid, they are not, just ask me. So because I know that we come from very different worlds, so it might sound obvious for someone or very non-obvious for someone else. And this is actually a TM, transmission electron microscopy image of a graphene exfoliated really in a rude way when I arrived in IIT in 2011. I didn't have many facility. I didn't really have a lab. I was just there. I took some graphite. I started to do a very rude work. I came out with something on top of a TM grid. I don't even know how. And we imaged it, and it looks more of a canyon. That's a bit, the graphene bit, a bit not flat. It's not really wrapping up as the theoreticians were predicting, but it's not as beautiful as we have it today. So when we synthesize graphene on metals, we can choose different metals. Oh, this slide is not the one I wanted, so sorry, I'm not okay. So we can choose between different metals, and how we choose the ideal metal usually depends on the carbon solubility. We have to synthesize something that is carbon-based. We don't want too much carbon solubility, otherwise we will have a non-controlled growth. What does it mean? If you bring a metal up to high temperature and then you flow carbon on top as methane, we use methane. Methane is what we also have in the house. It's CH4, it has carbon. We can actually hope that our metal as a catalyst breaks the bonds of CH4, and then we have just C, that carbon atoms that are running on top of the surface, and at some point will form our hexagon. Okay? But if we have a metal that really gets impregnated by carbon very easily, what happens is that when we cool down, all the carbon comes up, and then it's just amorphous carbon around, so it wouldn't work. We need some metal that has really low carbon solubility, so that just catalytically active helps us to break the methane bonds, form graphene, but when we cool down, because our growth is finished and completed, we don't get carbon segregation in the surface. Okay, that's almost every metal, if it's not very high purity, has a lot of impurities. So we work with materials. When we work with material, we typically check what is the purity of that material. No? If it's 99.9, you think, oh, then you almost know foreign atoms. It doesn't, no, it's not true. For making a single layer, it's more than enough, even for making many more. So you usually prefer to work with very pure materials to avoid this. But it's not always true, because during my career I also discovered that sometimes having it a bit dirtier, it helps some processes. So we can grow nowadays. The normal way to grow graphene is take copper foil. Not specifically super pure, actually a pretty normal copper foil, and it works well, okay? But between copper and nickel,
copper 100 million. We can do it on nickel, no problem. It's just the quality will be lower. So if you're aiming at this super ballistic transport, perfect properties electronic-wise, you will not have them, okay? And there you have problem to control the number of layers. Here you can have a monolayer, no problem, with a little bit of bilayer islands. There you can have 3, 4, really difficult to control the number of layers. And then it gets chaotic. So you don't have a continuous layer everywhere, where you have 2, where you have 3, where you have 4. It's very difficult to understand. So typically that's the one where we synthesize. And what we do, well, actually I should have put an image of our reactor, but on top of there you can see a horizontal reactor over there. I also have a pointer. Why don't I use it? So you can see this, and you can see that usually you will have inlet with where the methane enters. You don't flow only methane, you also need to flow carrier gas like argon, hydrogen, and so on. Argon is a pure carrier, just a heavy fat atom which helps to push other atoms in. Hydrogen is more catalytically active, actually also can help reaction to happen. But usually you just put your sample here, so your copper substrate, for example, flow the gases, get high in temperature, up to 1000 degrees. That's when you start to have a catalytic reaction, and then basically grow graphene. That's variable parameters: pressure, time, temperature, and gases that you can flow with speed. That's basically what we were doing at very, very early time. We started to grow on copper foil because people saw that it was a cheap and easy way to do it. So it's a very similar foil to the one that you have in kitchen with aluminum. Yeah, it's really similar. It's nothing fancy. Then you start growing. These foils are polycrystalline. That means there are different crystal orientation. They're not oriented. So you will have polycrystalline graphene. That will mean hexagons, because graphene beautifully grows as an hexagon. So you just see little oxygen. Actually, I have one sample here. Oh, look at this. Just thinking. What am I going? If someone wants to see of those in presence, that's I actually brought it for another at a Nobel Prize party. I wanted to show but actually I don't see how much you see, but is a bit oxidized in some parts. So if you see inside, you see that something shiny, something not. You might see hexagon. That's for graphene. So we do it that is millimeter size. So it actually starts to become visible just because the copper underneath is oxidized. But it takes some time to see it. But anyway, I just thought that. So I mean, when I saw your like your sensor, your skin sensor, that the triangle, I thought, okay, maybe something similar to this. So on this, I can grow graphene or just transfer. Actually, I will show you graphene can be transferred very, very well. Well, if you actually just swing it around, you might see some hexagons inside, but it's not always easy. So you get these hexagons. Okay, we can do it up to millimeter size, but the point is like that there will be many hexagons, and when they join, they will be differently oriented because they are polycrystalline. That means with different orientation, and that means that electrons will fly very, very fast. And okay, that's when we do a complete growth. So the growth starts. Okay, I'm doing stupid things. Okay, growth starts like this, continues, and that's a continuous layer of graphene. Here, bilayers joining, but it doesn't get much more than that, even if you completely screw up with the time. So basically, what you will have where these different grains join is that the electrons will actually find defects and will not run so fast. So the mobility gets down, the electronic properties goes down. So it's not an ideal substrate. So you can actually take a very thick layer of copper, which is oriented, or you can work on the substrate, and that's what we started to do something like 10 years ago. So for example, if you image, sorry, I jump back again. If you imagine TM, you will see these grains, different orientation, different colors. That means that 1 micrometer, and then actually the electron is going to slow down. Here we worked a lot to make millimeter size. That's what you are actually seeing. So they can even get up to centimeter if you work. But there is no point in doing that unless you really have some cool experiment. And in this case, you will have very optimal transport properties because they can move for very large amount of space. So if you do electronic devices, then mobility can be really ballistic. But usually those are just popping up randomly on your copper. You don't decide where they are. So something IIT did, so my group did, and it was actually pretty successful in doing, I will just jump because it's too boring, is to define the points of nucleation. It's nothing genius. You can, okay, big discovery, big idea. But we were the first one to do it very, very well. That means putting some seeds, like you're seeding, on the copper, and we use chromium
because it actually survives up to 1070. That's the melting point of copper, but that's also the ideal temperature to really grow good quality graphene. And we make it in a way that these seeds act as nucleation points, and then we grow our arrays. Why one would do that? Well, because photonics and electronic devices always come up with a design. You have a mask, you know where your devices are going to be. So the idea would be to integrate in a production line our technology in a way that you can grow graphene only where you need it. Okay, so if you know that it's like a matrix for naval battle or something like this, you know where you're gonna need your graphene, you do it exactly there. Okay, also for pixel and stuff like this, you can actually decide where to have your material. And it actually came out pretty nicely. It's one of the few times where the idea comes out, practical realization comes out as the idea. So we started to make these hexagons and another additional interesting thing is that the chromium that is at the center basically sinks in within the metal during the growth. So at the end of the day, you don't have a trace of the chromium on your graphene. So the graphene is enough for all the CMOS application and basic application. If you want to do spintronics and you use magnet where even having a few atoms of magnetic elements might actually screw up the entire project, maybe that's not that clean, but it's clean enough, I would say. I mean, you might have a few. Yeah, so basically that is what we did, and that's what IIT got pretty knowledgeable, known for the flagship, and that's how we actually got a lot of budget because we started to sell our products to other partners in other fields interested in having deterministic graphene. But if you just have deterministic graphene on substrate, well, not useful. You only have on copper. So either you find niche application on copper, which is possible, but not really, or you need to transfer it, right? So the main then difficulty was to develop a proper transfer, which is a deterministic transfer. That means that you are able to laminate your graphene, not making it dirty, because when you transfer, inevitably you get your graphene contaminated. If you do it on wet, you will get some atoms of water, whatever, molecules of water, atoms of some sodium, if you use sodium. And of course, that is going to a bit diminish the purity material. So we had to find and develop a way to do it as clean as possible with patent different approaches. And the main way as we do it is basically we make a frame around our copper, basically deposit a membrane. Sorry, the frame is around the membrane, deposit a frame membrane on top of graphene, get it sticked. It's a polymer, so it actually sticks. And then use a solution and electrochemical delamination. So we just have an electrochemical process and graphene. The old way to do this was just to immerse copper within a copper etchant. Iron chloride, I mean, there are different ways to do this. And you basically just got the graphene floating, and then you fish it. In this way, we have a membrane, we can transfer, we can put on top of flexible, I mean, we put it on top of paper, we put it on top of substrate. So it's very handy and easy. and can be deterministic. Why? Because we can use a microscope with a micromechanical stage, and we can actually precisely put our hexagons where we want. So if we have, for example, a photonic waveguide and we have markers, we know exactly our graphene. So after doing this, we automatize within the Graphene Flagship with Extron, that is also the company that does the growth system, a tool to completely fill up a wafer. So we typically do not grow a 6-inch wafer of graphene because it's too large. You would need a temperature homogeneity very, very fine over too large area. That's something that the tools don't do. So we typically grow something that is 2 or 3 centimeter by 3 centimeter and arrays, for example, and then we populate an entire wafer with multiple dry transfer. So we just do a kind of stamping technique, right? And we automatize with Extron a stamping tool that is capable of just. And we proved this up to 6-inch. We proved this on different photonic, for example, platforms to make photonic devices, as we will show later on. And yeah, that's the tool we should get in our labs. Nothing fancy for you guys working on such sophisticated robotics. That's probably a stupid thing, but it took some time to make it proper. And yeah, basically now we have our wafers coded graphene. Why, when you transfer on top of different substrate, you always have to make sure that the material preserves integrity as a first thing and quality, of course, if you're really aiming at high quality kind of application. So for example, what we do, we look with Raman spectroscopy, which is a very common tool for people working in material science, and is capable of giving you an idea of the presence, quality, the effect of your material. So for example, here we were mapping, and the color scale tells us the width of a specific peak that tells us how good and how many strain inhomogeneity we have in our material. In this case, we see, oh, really, really minimum value. That means little strain homogeneity. That means really good transport. Really, really. Because if you have a lot of strain homogeneities in your 2D materials, your electrons will not move as fast as you want. Okay, so basically, the long story short here is that we proved that our graphene transfer on silicon dioxide, which is the typical technologically relevant substrate for electronics, photonics, it's very high, and very high means 10,000. Before I name 600,000, 600,000 is ideally when you encapsulate it with another 2D material or you suspend it. When you put it in contact with another material, you will have interaction with the other material. You will have dirty, you will have interfacial contamination. So the mobility will go down no matter what. If you buy graphene nowadays from any of the companies worldwide, mobility is usually 1,000, okay? For many applications, 1,000 is okay. For other applications where graphene might really make a difference, you need 1 order of magnitude more. So for example, us making 10,000 really meant the possibility to start to think about integrating in photonics for telecommunication, because their mobility is very relevant to avoid losses, to make a more size compatible design, not too big devices and so on. So there, that's when we said we have 10,000, we start to work on photonics. Yeah, that's just a refinement of it. So yeah, here we still didn't have 10,000, and here when we approached 10,000, now we have above 10,000, so it's good. Talking again about carrier mobility, so the mobility, how fast electron and holes travel, we also proved that if you encapsulate it, this is not something we prove, it's something known, but we prove the value. If you encapsulate graphene in between 2 hexagonal boron nitride layers, hexagonal boron nitride is the white brother of graphene. Graphene is the black brother, it's black actually, graphite, right? And boron nitride is white. And it's exactly like graphene. You have hexagons, only that instead of having carbon, 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 you have boron, nitrogen, and so on, okay? Same thing, same story, same structure, everything, only is not a conductor, is an insulator. When you do electronics, you always need
conductor, insulator, a semiconductor. Graphene is not really a semiconductor. So when you might have heard about, oh, graphenium inside, we're going to substitute silicon with graphene. I mean, that's never going to happen unless you really change something intrinsic in graphene. Graphene is a semi-metal, so it will always conduct similar to a metal. So in a way, you will never have enough state. In electronics, you need enough. Graphene is always on, in no way out, unless you modify it, and then it's not graphene. Boron nitride is insulator, completely insulator. So basically, you can start to think about making 2D electronics, only with 2D material, which will be transparent, flexible, and everything else. So in this case, if you actually use this kind of sandwich technique and you put graphene together with boron nitride, and they're very flat, they don't have strain homogeneities, they're all the same, they match each other, then the mobility are those 600,000 that I was mentioning. They were 600,000 until 3 years ago for exfoliated graphene, the one with the Scotch tape, the one of the Nobel Prize. But these synthesized bottom up, no way, it was never so good. But a couple of years ago, we demonstrated that it is identical. So nowadays, if you use the exfoliated material or you use the CVD, chemical vapor deposition, that the technique we adopt, the bottom-up one, is the same, okay? So basically, you don't have anymore the difference. That's when I say the material now is mature, because now the properties are as they should, and you could start proving some of the things that you have read in books, and you might think they are bullshit. So yeah, of course, this opens up also a world for quantum technologies, because you start to see quantum properties of the matter. So one of the, okay, how much time I have left, just so I calibrate? Almost nothing, 5 minutes. Okay, so, okay, I mean, I will not go too much in detail, but when I started to work on graphene, one of the major hallmarks of graphene was the quantum Hall effect. So quantum Hall effect, it's a peculiar effect that was discovered by Klaus von Klitzing in 1980, and for which he won the Nobel Prize a few years later. I was working in Max Planck Institute in his department, and although I'm a complete clueless person about quantum Hall effect, I mean, I know now something, but for being in the department of someone that discovered it, I was not working with him. I was working in the material department, so I was making material, I wasn't making quantum measurement. It was pretty hot topic, as you can imagine there. And when, at the time, Andre Geim, that was the professor winning the Nobel Prize for the discovery of graphene, was saying, oh, but graphene on silicon carbide is not really graphene because you cannot see the quantum Hall effect. So this is not really a graphene material. And Klaus von Klitzing was telling me, oh, Camilla, we have to prove that it is a 2D material because you have to see the quantum Hall effect. It's just too much dope. There are too many electrons. That's why you don't see it. So we worked to tailor the material, remove the excess electrons, and we saw the quantum Hall effect. After 10 years, I was able to see the fractional quantum Hall effect on the CVD grown and in a different way grown material, but finally mature, because that's the signature. So when we finally saw that little vertical 1/3 effect there, here, I was like, okay, that's kind of a cycle of my life coming to completion, because we're able to show that that's also now really mature. We see the fractional quantum Hall effect. And this opens up all a world of application for quantum technology, okay, because it is, in this sense, a quantum material. Okay, this I've done. I have not much time, so just let me go through application. And I will just do a very, very quick possibility, but now that I share a bit of the basic thing, maybe we can think about something together. So the major topic where I worked in the last year was integrated optical photonics. That means that we integrate graphene on top of waveguide and try to make devices for telecommunication. So either modulators to modulate the electrical sign into an optical sign, or photodetector to capture the optical sign into and convert it into electrical sign. Okay, and why working in photonics? Because the materials that actually used nowadays for this application are encountering limitation. As you might know, there is always ever increasing need for bandwidth. We need more bandwidth. We need it though, a less power consumption, less cost, smaller footprint, smaller devices, light devices, and so on and so forth. And the materials that are nowadays demonstrate used, they are actually limited in bandwidth. There is not much going further, okay? While graphene, it really has a property as for light absorption and conversion, it has the photothermoelectric effect, some effects that really make it ideal for this task with little power consumption. And it's small, it's light, you can have small devices. That's why people started to really put money into this. And a lot of companies, Ericsson, Nokia, Huawei, they really been working on graphene heavily in the last years, and our major finances come from them. But for doing proper devices, you need 10,000 mobility. We now have it. So yeah, yay, great, I'm so happy. And we made photonic building blocks, such as I said, modulators. In this case, we had to do a very complicated structure. We have graphene exactly on top of waveguide with the deterministic transfer. Then we had to put an insulating layer, and then again mirroring graphene on top of the hexagon. So hexagon, 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 hexagon. And then in that way, we have some open eyes, as you might see here. That means that we actually are getting some signal modulation properly. And then we got photodetector with a photothermoelectric effect. That means almost zero power consumption. So it works almost with no current in. Yeah, that was the video of the Mobile World Congress 4 years ago now, where together with other companies, we showed that it was possible to get some of this photonic communication possible. And for the first time, about that time, we demonstrated the first transmission and reception of signal done entirely with graphene. So a graphene modulator and a graphene photodetector, and they all did the job without need of any other material. So of course, on top of a silicon nitride waveguide, but with graphene as active material. So that was something we're very proud, and that's one of the few times when I said, oh, something we do works, because I see you get to see that every day. For us, it's never such way. So when I saw it, I was like, oh, that must be the apex of my career. Probably I will never see something working again. Yeah, we now got accepted this work. It should come out these days. It's a wireless transmission based on a photomixer. It's a graphene unit that does a bit of a complex job, and it works very nicely. And it's for next generation 6G kind of transmission, still early stage. We need to scale it up. Still, this is not scaled up because graphene is scalable, but we need HBN. HBN is not scalable. So basically, we still have it, but we have very tiny bits working. Okay, so. But for one of these, we got a project where we just needed a unit, and then for one unit it works. Last things, since you do some magnetic sensing, I thought it might be interesting to say that we can do all sensors. All sensors are used for in IoT or automotive for magnetic sensing. I don't know whether this could be of any use, but we have really an edge here because of the quality of our graphene. As of today, we have the highest sensitivity that has ever been reported for graphene-based sensor, which are actually a very, very good solution with respect to state of the art. So typically it's better. There are other problems that needs to be solved, but in terms of sensitivity at present is the best one. Yeah, we did also coating of copper wires. This is a very rude application. We just needed to coat graphene copper wires. Why? That was also a pretty long project, because you can increase electrical conductivity. But it would be stupid to think that just one single layer of carbon increases the electrical conductivity of something that is more than 1 millimeter in diameter, right? You can't change it. That's because when you grow, you actually increase the crystallinity of the copper. And then graphene passivates it in a way that it doesn't enter oxygen or stuff and is maintained. So basically you have higher electrical conductivity, not so much high, 1-2%, but high enough to save in copper. And you might know that copper industry, a lot of money. So even if you save a little bit of weight for companies like Baldassari, which produce a lot of copper, that means a lot of saving per year. So we had to try to make a graphene coating inline reactor so that they could put it in their production line. And the break-even would have been in 2 years, but still, I'm not sure whether this will happen because the flagship came to an end, and so we'll see. But anyway, this was the main idea. And the main thing also is aesthetic, purely aesthetic. If you just take this, now we have it in the house, even 3 years old, it looks pretty old, not so pretty. While here it still look very, very shiny. So just prevents oxidation, looks better. It's more aesthetically pleasant. Yeah, then there is still biomedicine, but I will not go into detail here. One thing though that I was too much, this I needed to cut and then I forgot, this quantum, but it gets complicated. I'll just would like to conclude. So yeah, maybe two things. One is that by twisting 2D materials in different ways, you can really make a lot of things. Now the hot topic is magic angle graphene, because you have superconductivity and can vary. It's really difficult to make this structure a proper rotation angle. Usually you have 1.1 degree or stuff like this. And so sometimes we were always saying, oh, maybe we could collaborate with robotic guys to help us to make this properly, because we do it, but we still do it by hand with a goniometer, yes? So it works. Actually, we got to see all the super cool properties, but it's a lot of work. Then we synthesize novel 2D material by encapsulation, super cool. 2D gold is semiconducting, right? If you make it a single layer, it's semiconducting. We were the first one to see this. But yeah, we are working towards different lines, and one of them would be for me, and my aspiration would be to collaborate with you guys on something that we might define. And I put something a slide, yes. So I know that with Daniele, I discussed a bit about, you know, in the past, photonic, 5G, 6G, I mean, making very difficult stuff that wouldn't be tomorrow, probably few years, if anything. But we can do sensing. We can transfer graphene anywhere you want. It's a light material. It's resistant. It might not be the best solution in the form we synthesize it for everything you do, but we might think about it. I've read about, wanted something to ask you, but I haven't asked you before. When you actually are able to move ErgoCap, when I was, you know, the other day, I mean, how you send the signal, I don't know. I read something about graphene sensing element put in the helmets that were very, very, very well behaving, and we can do much better than these guys. But but anyway, just ideas. So anything, guys, and then maybe we can do something together. Yeah, thank you for your attention.
I'm Fiona from I worked one life ago. Okay. One thing is that you mentioned this application. One first question is, have you ever measured the carrier mobility with the pristine samples that is as produced without any transfer step? And the second question is, have you ever tried to synthesize it on boron nitride directly?
Nice, very good question. This is almost like being at home. So yes, I basically, okay, for measuring the mobility, we need an insulating substrate. So we could only do it when synthesizing on top of insulating or semi-insulating substrate, meaning sapphire or silicon carbide. Today I talked to you about synthesis on copper, but we synthesize on sapphire, we synthesize on silicon carbide, we synthesize on different substrates. On those substrates, we measure mobility directly by making the transistor. And in that case, the mobility is not very good because the starting material is difficult to grow in. Insulators are usually more difficult substrate to grow high quality graphene. So the best mobility, they are usually approaching Well, there are 5,000, but on silicon carbide. Silicon carbide is a great substrate for growing graphene because it's oriented, it has carbon inside, so you don't need to flow any methane. But the problem is that you don't transfer it easily. So it's just there, it's stacked on silicon carbide. Mobility is decent because you don't have any transfers, so you don't get really graphene contaminated. On sapphire, we have about 2,000. That's after many years of work, getting from 100 to 2,000. Now we saw that with a bit more trick, it could be improved. For me, the objective is getting it at least similar to what we get with copper and transfer, so 10,000, okay? So on copper, we cannot measure it simply because it's on copper, and then it conducts through copper. So then you measure copper. The other question is, yes, we grew on HBN. There is really problem with HBN synthesis, so you have to use the exfoliated HBN. That means you take something like graphite, only boron nitride, and you exfoliate. And when you have these tiny bits of 50 micrometer large flakes, you put it in the reactor, you grow graphene. It comes out very nicely, high quality, but there is more. Usually it's 50 micrometer or something. But yes, it's possible to do it. We're just waiting for people. See, I synthesize other 2D material. I haven't said this today. I synthesize transition metallic chalcogenides like tungsten disulfide, moly disulfide, 2D topological insulator, other 2D materials. So it's not just graphene in my group. Today, I just wanted to make an easy way of creating a bridge. But boron nitride, we don't do. It's a nightmare to synthesize. So I'm just waiting for some more knowledgeable people to do it and provide me with. But it's really difficult to do that to the material specifically.
Well, thanks for the presentation. It's not what happens every day. I'm like all the time. And so one thing that I wanted to understand, actually two things. So you were mentioning a bit the difference between low quality, different. No, but I get it. And one thing that I wanted to understand is, in that case, chunks of graphene here, because I guess they are small. They're not like 2 or 3 centimeters. And instead, in your sample, you showed that samples, but in that case, the samples are really one layer. Not question that the coating, how stable they are. It takes to get off the coating, the application.
Yeah, so thank you for the questions. Indeed, about the dimension of the of the LP produced graphene. No, I always laugh with Francesco about this, but classic graphene. No, classic graphene is mine. Sorry, now I get offended. That's the real graphene. The other one are just trying to be a copy. No, okay. So anyway, usually from what I know, it's still in the micrometer range because you're starting with something and then you put it in a basically centrifuge kind of thing. So it just gets each shreds. So usually what I got is a few micrometer from them. For example, we tried also to use our graphene for coating the helmet for Momo design. But in that case, the effect wasn't as good because when you have several layers, it's just more easy to have a uniform coating. When you have one layer, first of all, you would need a very big synthesis approach. Right now, it's possible to do roll-to-roll technique, so square meters of graphene. I don't have the tool, but there is people in the world doing it. But yet, you might have some local issues if it gets broken. It's one layer. So yeah. About us, so I show you that we could do like up to 1 millimeter, 1 centimeter, or we grow on copper, but actually nothing prevents us from making 6-inch, yes? But when you make 6-inch on copper, usually copper is a foil, as you see, so it has natural waviness. So what means is that you will have not the same quality of graphene. In some areas, not continuous. In some areas, more like maximum with bilayer islands, because copper has a self-terminating growth. That means you don't get more than that. If you grow on other metals, you can get a thickness inhomogeneity. If you grow, for example, on sapphire, which we grow nowadays, we developed an approach to make it up to 6-inch continuous coating. You can have some thickness inhomogeneities where you have mono, where you have more bilayer. Yeah, depends on the substrate a lot. Silicon carbide depends which phase of the silicon carbide crystal you choose. You can have either 1, 2, 3 or 50 layers. So, you know, then it's not even more graphene unless it's rotated. I say that graphene is not more graphene when it's more than 10 layers if it's oriented like graphite azimutally. So you have the same orientation. If it's rotated, each layer electronically decoupled from the one before, so electronically it can be actually graphene, even if it's 50 layers, because you just measure the conduction of basically the few top layers. The last question, again, tell me. The coating. Okay, that's a very good question, and for this we could open like a 2 hours discussion. But for example, the copper cable, that's a pretty inherently bonded growth. I mean, you grow it on it, so you have some strength with the substrate. When you grow on a substrate, there is always either a very strong, you know, some substrates are interacting strongly. For a moire, you have strong forces that are holding it. In that case, it's very well attached. When you transfer on something and you transfer CVD graphene, the one I do, is not always, I mean, you can damage it because it's one layer. So anyway, if you just go with, when we did some coating for glasses, you go there and you scratch it, it's gone, right? You need to protect it. You can protect it with a transparent polymer. We do that like very often for other applications where you need to have a conducting layer. When you need to substitute ITO or other conductive layer, you can do it with graphene very well. Then you can put just a thin polymeric coating, transparent, and you have your function without damaging the graphene. Then, of course, if you talk about coating with inks, I mean, people has used it, as you might have heard, to coat like even boats, you know, like to avoid oxidation. In that case, it might be very well because it's thick. Then it becomes visible, though. And then you have, you know, it's always a trade-off. And then you have some kind of darker paint that you put on your stuff. It's kind of, if well properly done, well adhered. But I'm not a LP person, so I will not further comment on that because really I don't have the knowledge about my material. I will tell you, if you grow on it, it's easy, but it still can be scratched easily. If you transfer it, it's a bit more complex.
Any other question? No, I have just a curiosity. So the linearity of the energy of the graphene. Yeah. So, but what is the cause of that? Is the somehow peculiarity of the Pisa orbital, or it is a peculiarity of the Pisa, and the slope, it depends on what?
Well, it has a precise number on graphene. So basically, if you have carbon atoms, it is not, it should be around that value, yes? Then, though, you might have variation, because if you actually, you think about, I always think about electrons within the carbon atoms, like people, and if they have something around and they talk with someone around and they find a good matching, then things change. So, for example, for bilayers, if they are azimutally oriented and they are very much coupled, then in that case it changes, because it changes the dispersion, though. So, you know, you change the band structure. Pure graphene, it should be ideally about, well, a specific value, but you might be a bit more or a bit less, depending on how clean, how good, and everything else. Yeah, of the quality of the graphene, yes. In a way, yes. We don't do it every day. Why? Because measuring the band structure is something that very few people can do it, and we can do it because we have now installed in my lab some angular sulfate emission spectroscopy tools, which allows you to see the famous cone. So you actually can see the band structure of not only graphene, but many other materials, and you can actually evaluate the quality and really look at the electronic properties of a material. If you make a stack, you can see how the bands are aligned. So you can really make an alignment spectrum like those that you design and sketch in physics or electrical engineering. So, oh, yeah, you can really see it. It's beautiful, and you know, if anyone is interested in visiting, you will not see much because it's a huge UHV UFO that looks like bulky. But yeah, there inside you can measure the band structure. Thank you.
people connected.
You're welcome.